Stanford University.
Today we studied particles last time, the action for particles. We compared it with non-relativistic physics. Today we're going to study fields. Fields have you taken all of that down? We're going to begin studying field theory, not quantum field theory, but classical field theory. From time to time, I might look at an equation and say, you know, something about that reminds me about what happens in quantum mechanics, and point it out. But for the most part, we will not be doing quantum mechanics, just good old classical field theory. The classical field theory that you know most about is probably electromagnetism, electromagnetic waves, and their interaction with electrically charged particles. We're going to start even a little easier than that. It'll be an examination at the end of the class to tell me which field of particle physics you think I'm talking about. Okay. Nevertheless, I'm going to start. Well, yes. Sorry. Let's start with spacetime. Spacetime has always one time coordinate and some number of space coordinates. Mathematicians or mathematical physicists or abstract people can study spaces with any number of times and any number of spaces, but the physical world, even in those theories in which space-time may have 11 dimensions, 10 dimensions, 26 dimensions, however many you like, it's always one time dimension. Nobody knows how to make logical sense out of more than one time dimension. So, and I don't want to get into now why that's true. The fact is, I don't know why it's true. But when we think about space-time, of any dimension, we think about one time dimension t and some number of space coordinates. Let's call them xi, where I runs over however many there are. And what is a field? A field is a variable, an observable variable, a measurable quantity, which depends on space and time, which varies from place to place, varies across space, varies with time. Could be electric field. Let's think of some examples of fields. There are some just from common garden variety physics. The weather. When you think about the weather, you can think about the temperature. The temperature varies from place to place. It also varies from time to time. So the temperature is a function of x and t. It's a field. Other fields, the wind velocity. The wind velocity varies also from place to place. It may also vary in direction from place to place, direction, time, and so forth. The wind velocity is also a field. The wind velocity is different than the temperature. The wind velocity is a vector field. It has a direction as well as a magnitude. The temperature is a scalar field. Scalar is a word for a thing which has a magnitude, doesn't have a direction. Okay, it has one component, whereas a vector field, an ordinary vector, has three components. In relativity, vectors have four components, but we'll come to that. All right, so we imagine then some kind of field. The field is a function, let's call it f, phi. Phi is the Greek f, and the generic field is often just labeled with phi of x and t. We'll be thinking for tonight mostly about scalar fields. Now, let me come over to this blackboard over here, and in parallel, think about something else. I want to think, just in parallel for a minute, I want to think about the motion of particles in non-relativistic physics. Not the relativistic motion of particles. I want to think about the non-relativistic motion of particles. Here's how we think of them. We draw a time axis. Now, we're used to drawing the time axis as vertical. I'm going to draw it for the moment as horizontal, just to indicate, because I want to think about functions of time. And in thinking about functions of time, I want my independent axis to be time, horizontal. And the thing I'm going to plot is the position of a particle. A position of a particle along, let's say, a one-dimensional axis. And what do we call that axis? What's a good name for that axis? Why? Why? Why not x?
Or s for displacement.
I'm not going to call it either one. I'm going to call it by the stupid term phi. Why? Phi. Phi. Pho. That's the coordinate position of a particle. So, and of course, I have a perfect right, a mathematical right, to call the position of a particle phi. I don't have to call it x. I don't have to call it anything I want. And then what is the motion of a particle, or the history of the motion of a particle? It's a curve. It's a curve which tells you what phi is at every point of time. It can go negative, it can go positive. There it is. And how do we describe it? We describe it by the principle of least action. The principle of least action, let's write it down now. What would the principle of least action be? Well, we know that first of all, we express it in terms of a Lagrangian. The action is equal to an integral from some initial time to some final time, let's say from A to B, of some Lagrangian dt. And for simple non-relativistic particles, there's a very simple Lagrangian that we write down. It's the kinetic energy minus the potential energy. So what is the kinetic energy? It's 1/2 mv squared. 1/2 the mass of the particle. Let's put m over there. And what's the velocity? Phi dot, right? Not x dot, not t dot, but phi dot. Phi is the coordinate. So we would write phi dot squared, or d phi dt squared. We could write it as d phi dt squared. Let's write it that way. D phi dt squared and then we might put some potential energy in. Let's put some potential energy in. That would be minus the potential energy as a function of what? Phi. Okay. Phi. dt. The Euler-Lagrange equations, let me remind you what they are. This, of course, this object in here would be called the Lagrangian. The Lagrangian is m over 2 phi dot squared minus v of phi. And the equations of motion are given by d by dt of the derivative of the Lagrangian with respect to phi dot equals the derivative of the Lagrangian with respect to phi. This is the force on the right-hand side, and this would be mass times acceleration, acceleration being phi double dot, the second time derivative. So if we worked it out, we would just get Newton's equations here. Okay, well, maybe we'll write it down. M phi double dot equals minus dv d phi. That's Newton's equations. And that's the net upshot. Oh, but just one more point that's worth pointing out. The action principle, or the Euler-Lagrange equations, are the solution to the problem of finding the trajectory with the minimum action, or I'm going to use the term minimum, but you know very well that I mean stationary. Could be maximum, could be minimum, but let's call it minimum. The minimum action of a trajectory from here to here, holding these points fixed. Holding point A and point B fixed, find the trajectory of least action that connects them. That's equivalent to the Euler-Lagrange equations. And the way that I like to think about it, I think we worked this out last time, is you divide the time axis into a lot of little pieces. And instead of thinking of the Lagrangian, or instead of thinking of the action as an integral, just think of it as a sum of terms. And what do those terms depend on? They depend on phi at each time. In other words, the total action is simply a function of a lot of values of phi. It's some function of a whole bunch of values of phi. How do you minimize a function of phi? You differentiate with respect to phi. That's what the Euler-Lagrange equations are. Another way to say it is they're the solution of the problem of moving these points around until you find the trajectory which minimizes the action. Okay? So that's non-relativistic. This is non-relativistic. It's not the relativistic particle theory. The non-relativistic description of particles in a force field. Now, let's come back over to here. Here, phi stood for a field which is a function of time and space. How many space coordinates are there? Well, in our world, there are 3, but we can consider worlds with 10 dimensions of space, 9 dimensions of space. It's even interesting to think of worlds with 2 dimensions of space. That would be this tabletop. Things can move around on the tabletop. That's a world of 2 dimensions. Okay. You can even think of a world with 1 dimension of space. And time, of course. 1 dimension of space could be beads moving up and down on a wire. Particles, like bead-like particles moving up and down on a wire. Okay. But you can even think of 0-dimensional space. 0-dimensional space means a point, but what would the corresponding space-time be? It would have a time and no space. Imagine a world now with time and no space. Okay? And a field. In each case, the field was a function of the time coordinate and whatever space coordinates there happened to be. If we go down to this limit, this strange limit where space has no dimensions at all, but only time, then we're talking about a theory of a function of time. That's all we're talking about. This is a theory of a function that only depends on time. So you see, you can think of ordinary particle mechanics as a field theory in a world which has no dimensions of space, only a dimension of time. Instead of thinking of the field, instead of thinking of phi now, the same mathematics, but a different interpretation, instead of thinking of phi as the position of a particle, think of it as a field which depends only on time. Calling it a field is just a name. You could call it the coordinate of something, you could call it a field, you can call it whatever you want, but it's just a function of time, and I'm going to think of it now as a field in a world with 0 space dimensions. Yeah.
So does the potential vanish in that case?
No. No, it can still depend. No, that would be a term in the energy which would depend on the value of phi. You could imagine a field, and you could imagine that the potential energy in the field depends on phi. That it costs energy to change phi. Now, in the back of your mind, you can remember that phi stood for the position of a particle, if you like. To say there's a potential energy just means that if you move this curve up and down, the energy changes. That's all it means. We of course, are not going to think of phi as the position of a particle. We are going to think of it as a field, and we're going to go in the other direction. We're going to generalize from this pattern over here. This was a field theory in a world with no space and one time direction. We're going to generalize to a field theory with a time direction and a collection of space coordinates. The field now is not just a function of time, it's a function of space and time. Phi of x and t. Well, I don't have to write it again. There it is.
Is it the same thing conceptually to think of phi as a function of time in a world with no space coordinates, or to me it's more compatible to think of it in a world with space coordinates but only dependent on time? Is that the same thing?
You could. It wouldn't matter. It's very hard to visualize a world without coordinates. So think about it as a world without coordinates in which nothing depends on position, only on time. It's fine. Okay. Right. It doesn't matter. All right. So now, let's try to guess what the principles of mechanics, not the principles of mechanics, but the principles of field theory are, knowing what the principles of field theory are in a world with only one time. And our best guess, my best guess, somebody's best guess, wasn't mine, is that the world should be governed by a principle of least action. Least action was a very powerful principle in all of ordinary mechanics, not just for the theory of one particle, could stand for 2 particles, 10 particles, 1,000,000 particles, a gas, whatever. It was a very powerful principle which encoded and summarized huge numbers of laws of physics. And we're going to take it as a matter of given that, that field theory, in fact the whole world, is described by an action principle. All right, now what does an action principle look like? Now the world is not just a line. The vertical axis now I don't have enough dimensions on the blackboard. I'll try to draw you a picture, but on this side of the blackboard, I am going to plot time vertically. Don't get confused. Time is still time. But horizontally, I'm not going to plot phi, I'm going to plot x. This x could stand for 3 or 4 or 2 or however many x's there are in the problem. In a simple problem, there might just be one time and one x. That would be the problem of the world on a line. And phi, I don't have enough axes to draw it, but phi would just be a field which has a value at every point of space and time. Oh, I can draw it. Here, we'll draw it this way. T goes this way. X goes this way. This is intended to be a drawing of a horizontal plane. And the value of the field, whatever it is on the vertical axis. Then how would I draw it? Would I draw it as a curve? No, it's not a curve, it's a surface. It's a surface. Above every point, or at every point, the field, phi this way, the phi has a value, and so if I wanted to draw the whole history, just as I draw the history of the particle here, or the field, the one-dimensional field, if I wanted to draw the whole history in space-time of the field, I would draw it as a surface here. So that above, and of course when I say above, it could also be below. The field can get negative, no reason why it can't be negative. But above every point, there would be a value of the field. At this point, phi is here. At this point, phi is over here. Move back a little bit, and phi is up here. And that would describe a two-dimensional world. This would be a world with one space and one time. In the lingo, incidentally, the dimensionality of space-time, our space-time, is called 3+1. 3+1 means 3 dimensions of space, 1 dimension of time. This would be a 1+1 dimensional world, 1 space direction, 1 time direction. And if we added in the field phi, the history of the world would look something like that, or the history of this field would look something like that. Now, of course, I'm not going to try to draw what this would look like in 4 space-time dimensions. I can't even draw 4 space-time dimensions, let alone put in another dimension to describe the field. But you get the idea. Okay, now what about the action principle? In this case over here, we bounded the time axis between 2 points and asked for a curve which minimized some action. The analogous thing in field theory is to bound the space-time, for example, by a rectangle bounding both a region of space and time. Over here, it might be a rectangle like this. And talk about the field within the rectangle. Talk about the field within the rectangle, just as we talked about the field on the interval between A and B. Now, let me just remind you, I should have mentioned it while we were talking about the action principle over here. When I said you minimize the action, there's something that you hold fixed. Do you remember what it is you hold fixed when you minimize the action? The endpoints. You freeze the endpoints, you don't let them move, and you say, what's the minimum action subject to the condition that the endpoints are fixed? This is very much like asking for the straightest, for the shortest distance between 2 points is a straight line, and you hold the endpoints fixed, and you look for all the ways you could wiggle the curve to minimize the distance between them. In the same way, or in a similar way, the action principle says, hold fixed the value of the field on the boundary here. It doesn't have to be a rectangle. It could be any space-time region. Take a space-time region, freeze the field on the boundary. Okay, so that means it's sort of frozen over here. Here's a boundary. My diagram is getting too cluttered. But we hold the field fixed on the boundary and then let it wiggle up and down, or let the value of the field phi of x and t wiggle until we find a configuration that minimizes the action. And that will be the history of the field in space and time. That will provide for us a set of equations of motion. Okay. You get the idea? If not the details? The details can only be provided by telling you what the action is. Right.
Just clarification. So the Lagrange formulation still works if the potential depends on time?
Oh, yes, it does. Absolutely. Yeah. The analog would be something depending on space and time here. Yeah. Yeah. Lagrangian still works. What doesn't work? What doesn't work if the Lagrangian depends explicitly on time?
Energy conservation.
Energy conservation. Right. But the Lagrangian formulation does work. So does the Hamiltonian formulation. It's just that energy is not conserved. Okay. And the same thing is true here. Yeah.
Is the boundary just the bottom and the top of that rectangle, or the whole rectangle? Or
the whole rectangle. The whole boundary of the rectangle. All 4 sides. Right. Just as in this case, we bounded it at the 2 ends. We bounded it at the 2 ends. Here we bound it. And we hold fixed the value of the field here and let it wiggle around. All right, so how would we in practice do this? First of all, we would need an expression for the action. The expression for the action will be, just as it is here, it was an integral over time In other words, a sum of terms for each one of these little segments here. We're going to assume that the action is a sum of terms, one for each cell, if we divided this thing up into tiny cells. In other words, that it's an integral over space and time. So we take our region that we're interested in, we break it up into a lot of tiny little cells. This is, of course, just a trick to implement doing an integral. An integral over x and t is just a sum over all these little cells. And in each cell, we specify what the action within that cell is, and then add them all up. Okay. That's the same sort of thing that we did here. We thought of the action as a sum over little infinitesimal cells. So the only other question then is, what shall we take for the Lagrangian? Okay. All right, so there's a set of rules. The rules are quite similar and generalize the mechanics of particles. It's almost a direct generalization. First of all, it should be an integral. So the action is an integral, but it's an integral not only over time, but of space and time. dx dt. How many dx's? However many coordinates of space there are. So we can write this as dx, let's say dy dz. I don't have enough room here. dx dy dz. But in relativity, we've learned to sort of think of the four coordinates on a sort of common plane as being all parts of space-time, and just give them a name. All four coordinates, call them x mu, where mu runs over four values, time and the three components of space. And so it's frequently it's not just frequently, it's standard to write the integral over all four coordinates of space as just integral d4x. Of course, if we were dealing with a theory in 5 or 2 or 1 dimension, we would replace this by d2x, d4x, d1x. What would x be if it was only 1 dimension? It would be time, right? So d4x includes dt, but it also includes the directions of space. All right, but you can just think of it as dx, dy, dz, dt. And then some Lagrangian. Now this Lagrangian is something, as I said, which isn't just to be integrated over time, it's to be integrated over space and time. It's often called the Lagrange density, but it's just the analog of Lagrangian here. And what does it depend on? Well, of course, it's supposed to be a Lagrangian for the field phi to tell you how phi behaves. So one of the things it's certainly going to depend on is phi. That's the analog of saying the Lagrangian, we didn't say it over here, but that's the analog of saying the Lagrangian over here. It depends on phi. Depends on position. It may or may not depend on position, of course. But it also depends on the derivatives of phi, in this case with respect to time. If time and space are on the same footing in relativity, we might expect that the Lagrangian depends not only on the time derivative of phi, let's put it in there, d phi by dt. But if it's going to depend on d phi by dt, and we're dealing in a theory of relativity where time and space are on pretty much the same or very closely related footing, we might expect it also depends on the derivatives of phi with respect to x, with respect to y, with respect to z. And however many more coordinates there are. That's the Lagrangian. The Lagrangian is a function of the fields phi, there may be more than one field, incidentally, just as in this situation over here, a particle may have more than one coordinate locating its position. It might be x, y, z, and so forth. There may be more than one field, but for the moment, let's just concentrate on a problem with one field called phi. Then the Lagrangian depends on the field and its various derivatives.
Doesn't it depend on x, y, and z too?
It might, just as the Lagrangian might depend on t over here. It might. Now, for a closed system, ordinarily, a system which has an energy conservation, it means that the Lagrangian doesn't depend explicitly on time. And the same would be true here. It would not depend explicitly on time or space, but it could.
Is what we're developing here for the case of phi a scalar field, or in general for?
At the moment, I haven't. So far, I haven't said anything that makes it a scalar field, other than the fact that I only wrote one component. If it had been a vector field, I would have to have some more components. But if it's a scalar field, then it would only have one component. So yes, I certainly have in the back of my mind here a scalar field. But up till now, it doesn't matter. I mean, it could be anything. All right, so let's condense notation. Let's just write this as a function of phi, and the collection of derivatives d phi by dx mu, of which there are several, time derivatives and space derivatives. We could even condense the notation a little bit more. For time derivative, we would use phi dot. What would we use then for space derivatives? Well, the nice condensed notation is not to use this. The nice condensed notation is to write phi sub t, phi sub x, phi y, phi z. And these things mean, by definition, the derivative of phi with respect to time, derivative of phi. So this would be d phi by dt. This would be d phi by dx, and so forth. That's a more or less standard notation to put a little t or an x or a y or z here. And we could, if we liked, write phi sub mu, meaning the derivative of phi with respect to x mu. But I won't. I'm going to leave it the way it is, d phi by dx mu. And what's our problem? Our problem is to solve the problem of fixing the field on the boundary and wiggling it around, wiggling it around until we find the configuration that minimizes this action. If we replace the space and time by a grid like this, let's just think about how we would do it in practice. We would replace the space-time by the grid of points. We would replace the Lagrangian. It would depend on phi at each point. But what would we replace d phi by dx with? Little differences. Little differences. All right? And in the process, we would actually write this action as a function of the values of phi at each grid point. It would just be a function. It would be a function of a lot of variables. How many of them? 10 this way and 8 this way. It would be 80 variables there. Something like that. A lot of variables. The finer we make the lattice, the more variables. But it would just be, the action would just be a function of some collection of variables. And how would we minimize it? We would minimize it by differentiating the function with respect to the variables and setting it equal to 0. Exactly the same operation that we did over here. Doing that operation, and it's in your notes, in your classical mechanical notes, in the classical mechanics notes, we went from that principle to the Euler-Lagrange equations. The Euler-Lagrange equations, in fact, written in this form here, minus this equals 0, is basically the equation which says differentiate the action with respect to phi at each point and set it equal to 0. That's what this was doing. Took a few steps. We worked it out. The question is, how would that change if we have this multi-dimensional analog of exactly the same thing? Multi-dimensional analog of the same thing. And the answer is, it would change, but it would change in a rather recognizable way. I'm not going to work it out. We're not going to derive it. I'm going to write down for you what the equations are, which are the equivalent of saying that the derivative of the action with respect to phi at each grid point is equal to 0. Okay, that's what we would do. The corresponding Euler-Lagrange equations. I'll write it and then I'll just show you what the correspondence is. Well, no, let's rewrite the ordinary Euler-Lagrange equations over here, and then I'll change them. Originally, it was d by dt of partial of L with respect to d phi by dt. We differentiate the Lagrangian with respect to d phi dt minus the derivative of Lagrangian with respect to phi equals 0. That was the naive, not the naive, but the simple version in which there was only one coordinate of time. How does it change? It changes in a very simple way. Instead of having a single term here with a time derivative, you have a sum of terms, one for each direction of space-time. And that term looks like, each term looks like a derivative not with respect to t, but with respect to x mu. Now, one of the terms will correspond to t. X mu runs from t, x, y, and z, a sum over mu, one for each direction of space-time. The derivative of the Lagrangian with respect to what? What would you guess? One possibility is that it's just d phi by dt. No, that's right. It's derivative of phi with respect to x mu. In other words, you go and you look for the particular term. Here's a particular term, for example, d by dt. There's one term which is mu equals the time component. It would read d by dt of partial of L with respect to phi dot. But then there would be another term, plus d by dx of the derivative of the Lagrangian with respect to d phi by dx. And then another one for y and another one for z. That's what happens to this term. That's all. The other term is even easier. It's exactly what it was before, the derivative of the Lagrangian with respect to phi. And that's equal to 0. That's it. Those are the Euler-Lagrange equations that the solution to the problem of finding, of course, it doesn't solve the problem of finding the history of the field. What it does is it reduces the action principle to a differential equation, or a collection, well, a differential equation. Let's do it before we discuss relativity and the constraints of relativity. Let's do it for a simple example which is patterned on the same structure over here. Incidentally, what we're doing here, I'm calling it field theory. It has another name. It's called Continuum Mechanics. Continuum mechanics, it could apply to a lot of different things. It could apply to the flow of fluids. It could apply to elasticity. If it was elasticity, then the degrees of freedom might be the displacements of points in the elastic material. If it was fluid, the degrees of freedom might be the fluid velocities and so forth. So what we're doing here is called continuum mechanics, really.
And this would work for a world where there is only space and no time as well, right?
Say it again?
For a world where there's only space and no
Oh,
time.
yes.
It's just the d phi by dx mu where x minus t will be 0 for that world.
Yes. Now, when does that ever occur? Okay, so that's exactly right. Those are the equations that you would write down if you were looking for a solution of a field theory in which nothing depended on time, in which everything didn't change. In other words, if you were looking for what's called a static solution of the equations of a theory. If you had a feeling that there was a solution of your theory, for example, a time-independent electric field or magnetic field of a donut-shaped solenoid or something, okay? And you were looking for a solution which was not time-dependent but which was static, you would then say, you would look at the equations and say, let's throw away all the time derivatives here since we're looking for a solution which is static, and then we would only have the same equations but with just the space components. Right, so that's a good point. But let's try to build us an example, study the example a little bit, see what kind of equations we get before we enter into the discussion of the implications of relativity. Okay, here we go. We're just going to take this thing over here and generalize it a little bit. Instead of just saying that the Lagrangian has an m over 2 times phi dot squared. M is just a number, incidentally. Don't think of m as anybody's mass in here. Just think of it as a number that you could put into a Lagrangian. And since it's just an arbitrary number, I'm going to set it equal to 1. Just 1/2 phi dot squared. All right, what would the generalization be? The generalization, here might be a guess. That the Lagrangian contains d phi by dt squared. We'll put the 1/2 in. But we don't expect it to only depend on time derivatives. We also expect it to depend on the space derivatives. So a simple possibility would be d phi by dt squared plus d phi by dx squared plus d phi by dy squared plus d phi by dz squared. I'm going to stop writing out all x, y's, and z's in a little while, and that's something we could write down. Does that sound right?
No.
Why?
You want something that is relativistic to the invariant.
No, we haven't gotten to relativity yet. We don't care too much about relativity yet. Let's not worry. You're right. Of course you're right, but let's not worry about the details of relativity. You're right, but let me just make it a little more primitive than that.
Okay. The units are wrong.
Nah, that doesn't bother me. Put a C someplace, doesn't matter. Sorry. That was not what I meant. If this were the Lagrangian, it would be completely the same for space and time. There would be no difference between space and time. That just doesn't sound right. It doesn't sound right that the behavior of waves can't tell the difference between the time coordinate and the space coordinate. The world doesn't work that way. Something different about time than space. We recognize it. What's the right answer?
Minus.
We'll come to why. And of course, the why does have to do with exactly what you said. It has to do with, but exactly the same kind of Lagrangian. Incidentally, if we were doing relativity, there would be some speeds of light in here. Anybody figure out where the speeds of light go? I can never remember whether it's c squared multiplying this one or c squared multiplying this one. That's units. Right. C goes with T, so we might put a 1 over C squared in front of this one here. 1 over C squared. But this might not be light. It might be sound. Or it might be elastic waves in a solid. Then what would we replace this with? Sound velocity. Or the elastic wave velocity or whatever.
What should be the V part of it as well, the potential part?
What's that?
The kinetic part plus minus the potential part. You need to add it to the end of that.
Yes, you can think about it this way. You can think of this as part of the potential energy. Officially, the definition of kinetic energy has to do with time dependence and kinetic energy, and potential energy has to do with everything that doesn't depend on time derivatives. So since we typically subtract potential energy, that is part of the connection. But ultimately, the real reason is relativity. Now, we could add to this, if we like, minus some V of phi. Potential energy, which is there just because the field has a certain value. Potential energy in each little square there, potential energy or potential term in the Lagrangian, which only depends on V of phi. So that's an interesting case to explore. Let's try to explore that and see what kind of equations of motion we get from it. Let's take this Lagrangian and work out its equations of motion. This is part of the Lagrangian here. The whole Lagrangian is all of this. All right, first step. Calculate the derivative of the Lagrangian with respect to, let's start with the time component here. Let's start with the time derivative. Partial of L with respect to phi dot. What is that? Can you read it? It's just phi dot, right? Derivative of this Lagrangian with respect to phi dot is just phi dot. Phi dot meaning d phi by dt. That's the derivative of the Lagrangian with respect to phi dot. And then we're supposed to differentiate that with respect to time. So that becomes, on the left side, the second derivative of phi with respect to time squared. It's analogous to the acceleration. In fact, it is the acceleration of the field, d second phi by dt squared. Now, we do the same thing with x. We're supposed to sum this over t, x, y, and z. And the only difference when we do it with respect to x will be that sign, that minus sign. I haven't put, I could put in the speed, we could put a 1 over c squared here. Let's put that velocity in. And as I said, that velocity could be the speed of sound, it could be the speed of water waves, it could be the speed of whatever kind of waves we're talking about, whatever kind of thing we're talking about. d second phi by dt squared. And then what happens for the space components? The space components are exactly the same except with a minus sign. d second phi by dx squared. And I won't bother writing y squared, z squared, and so forth. Or minus dot dot dot. That's this term. And then minus dl by d phi. Minus derivative of the Lagrangian. Now, does the Lagrangian depend on phi? Sure it does, if there's a v of phi. If there is a v of phi, then we would have minus or plus dv by d phi. Two minus signs. One minus sign becoming, because the Lagrangian is minus v, and the other minus sign coming from here. Equals 0. I'm thinking. Ah, got it. Yeah. All right. Let's start with a case where V is 0. Well, I think you've seen that kind of equation before. This is a wave equation. This is an equation for a wave moving along the x-axis. I don't think we want to solve it tonight. It's not our business. I think most of you know that this corresponds to waves which can move up and down an x-axis with the speed of light or with the speed c. And so we see how wave-like motions come out of the same kind of Lagrangian formulation. Let's suppose that we put back the v of phi, but I'm going to put back a particularly special kind of v of phi. I'm going to put back in a v of phi which is equal to 1/2 a quantity which I'll call mu squared. It doesn't mean anything now other than a coefficient here, times phi squared. What would this be in the case of ordinary classical mechanics, where phi really stood for the position of a particle?
Spring constant.
Spring, yeah.
What? Yeah, you said it, I think.
Spring constant.
Spring constant, right. This would be, you know, mu squared times the displacement of the, this would be a harmonic oscillator with a spring constant mu squared and a quadratic potential energy, you know, like 1/2 kx squared. That's what this would be. And so one might think of this equation. Now let's see, this is plus m, where did I write it? Mu phi squared, right here. Plus, not mu. We want dv by d phi. dv by d phi is mu squared times phi. You might think of this as a higher dimensional version of a harmonic oscillator. If this term weren't here, it really would be just a harmonic oscillator. Acceleration plus a coefficient times displacement equals 0. It'll be an ordinary harmonic oscillator. Now this makes it more complicated. It's some sort of wave-like motion. And of course, when I wrote d second phi by dx squared here, you might have imagined that there was other terms, d second phi by dy squared, and so forth.
Why did you drop the half there?
Over here? Because the derivative gets another factor of 2, right? Derivative gets another factor of 2. That's why the 2's are put in there, so that they disappear. It is the same for the harmonic oscillator. The potential energy is always defined as 1/2 kx squared, just so the force is kx. Right. All right, well, that's field theory in a nutshell. But now, or continuum mechanics. But now we want to discuss its connection with special relativity. When we built ourselves a theory of particles, there were basically 2 principles in addition to the least action principle. Least action principle and 2 other ingredients. The first is that the action is always an integral. And for the case of a particle, it's an integral along the trajectory. All right, we've taken care of. Here it's an integral over space-time. The other principle is that the action should be the same in every reference frame. It should be built out of quantities in such a way that it has the same exact form in every reference frame. How did we manage that for the case of a particle? Well, first of all, we built it up out of a lot of little segments, but we chose for the action of a segment a quantity which was an invariant. You remember what it was? The proper distance or the proper time along the trajectory. And since everybody agrees about the value of the proper time, the invariant proper time for a little segment, when you add them up, everybody will agree about the value of the action. They'll all express it by the same set of rules. And so the equations of motion, when you derive them in one coordinate system, will have exactly the same form as they have in any other coordinate system. In other words, the laws of mechanics, particle mechanics, will be invariant. Same in every reference frame. We want to do exactly the same thing in field theory. We want to add the ingredient. We've actually already done it, but we want to spell it out now. That implies that the laws of field theory, and for a specific field theory here, are Lorentz invariant. All right, so to that end, we have to know how to form invariant quantities, integrals like this, which are invariant. To do that, we have to know how things transform. We could not have done this case here if we didn't have a transformation law for the coordinates or for the dx's. Dx along here, how do dx's transform under a Lorentz transformation? They transform as the components of a 4-vector. Once we knew that, we knew that the quantity d tau squared, which is equal to dx dt squared minus dx squared, we knew that this was invariant. But we had to start with a quantity whose transformation laws we knew. In that case, the transformation laws, or the Lorentz transformations, applied to coordinates, and they also apply to differences of coordinates, and they apply to differential little bits of coordinates here. That was the guiding principle. Construct things which are invariant, which are the same in every coordinate system. All right? So we have to start with a collection of objects which are coordinate invariant. All right. That brings us to the nature of the transformation properties of fields. Fields are functions of position. One kind of field would be like the temperature, just a thing which doesn't transform at all. All observers, no matter how they're moving, no matter how they're, whether they rotate coordinates, whatever you do, the temperature is the temperature. Now, actually, temperature is a little bit funny. If you actually took a moving thermometer, moving through the atmosphere, it probably would not register the invariant temperature. So it's not really a good example. But a scalar quantity is one which, no matter what frame of reference it's looked at from, or what coordinate system it looks from, it's always the same, called a scalar. Scalar doesn't change when you either rotate or Lorentz transform coordinates. You can say it this way. You can say that the value of phi at a point x, and x now stands for x and t, is exactly the same as the transformed field phi prime evaluated at the transformed coordinate. X could stand for position in space-time in your frame. X prime and t prime could stand for position in my space-time position in my coordinate frame. Phi is what you call the field, just a name you give to the field, And I call it phi prime, just because I'm the primed person. Okay? Here's a point in space-time. You call the value of the field phi of x. X, as I said, x stands for x and t. I call it phi prime of x prime. But it's just one point, and it's the same field. It's the same value. It's just an invariant quantity. And so the transformation properties of scalar fields are just, they're equal to whatever they're equal. Next, in importance of vector fields. Now, these are not 3 vectors. These are 4 vectors. They have 4 coordinates. We've already seen, we have 4 components. We've already seen some examples. Just displacement, x mu, displacement from the origin, is a 4 vector. Differential displacements between neighboring points, dx mu, is a 4 vector. If you multiply 4 vectors by scalars or by invariants, you get back 4 vectors. Okay, because invariants, they're completely passive when you transform. We already know an invariant, d tau. So if you take dx mu by d tau, which we called the 4 velocity, that's also a 4 vector. What does it mean that it's a 4 vector? It's a statement about how it transforms under Lorentz transformations. Let's write it down. Let's write down what the transformation properties are. It's just Lorentz transformations. If we consider 2 coordinate systems moving past each other along the x-axis, then we know that t prime, well, let's start with t prime. T prime is equal to t minus vx over square root of 1 minus v squared. X prime is equal to x minus vt over square root of 1 minus v squared. Y prime equals y, and z prime equals z. Right. Things which transform in this way, complexes of 4 quantities, a time component, an x component, a y component, and a z component, things which transform in this way are called 4 vectors. So this is also true for dt, for a differential displacement. Where the differential displacement might be a differential displacement along a trajectory. It's also the transformation property for the 4 velocity. If you divide by d tau, it tells you how the 4 velocity components transform. Anything which transforms this way is a 4 vector. I need a name, a generic name for 4 vectors. I would use v for vector, but v is also already velocity. So we could use a, but a stands for the vector potential. I would use b, but it stands for the magnetic field. C is the speed of light. D is for derivatives, E is energy, F is force. I've run out of letters. So I'm going to stick with A. A.
A for arrow.
A for what?
Arrow.
Arrow. Arrow, good. Arrow. Right. But later on, it will have it'll be a, right. So a 4 vector has 4 components. We can call it the time component, but we're used to calling it a naught. A x, a y, and a z. And the transformation properties of these things are, in my coordinate system, I call them prime. They're equal to the values in your coordinate system, a x minus v a naught divided by square root of 1 minus v squared. Notice a naught is the same thing as the time component, so it's ax minus v at. What about this one? Did I write that correctly? No, I did not. A naught minus ax. And this one is ax minus v a naught square root 1 minus v squared. This one is, this is the primed variable. This is the primed. This is the primed. An example of a field which obviously transforms this way. Can I give you an example, one that makes it clear why that transforms this way? Yeah. Imagine a fluid filling space-time. Imagine a fluid filling space-time so that at every point in the fluid there was a 4 velocity, an ordinary velocity for the fluid points, but also a 4 velocity. And the 4 velocity could be called u mu, but it would be a position-dependent thing. If the fluid was flowing, the velocity might be different in different places. The 4 velocity, this is u. Right, u. The 4 velocity could be thought of as a field. The 4 velocity of a fluid in space-time could be thought of as a field. And since it's a 4 velocity, it's a 4 vector. It would transform in exactly this way, except we would call it u instead of a. The value of u in your frame would be different than the value of u in my frame, the components, and they would be related in this manner here. But there are lots of other things which could be 4 vectors. I won't try to tell you any right now, but a 4 vector is a possible kind of field. So 4 vectors are a mu, also of x and t. And they transform in this manner here. Okay. You can make scalars out of 4 vectors. If you take the 4 components of a 4 vector, you can make a scalar out of them. In fact, if you take any 2 4 vectors, you can make a scalar out of them. But let's just stick with 1 4 vector. You can make a scalar out of it the same exact way that we made a scalar out of dx mu. The tau is equal to, or the tau squared is equal to dt squared, blah, 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 minus dx squared minus dy squared minus dz squared. In the same way, every 4 vector can be used to make a scalar, and it's just a naught squared minus a x squared minus a y squared, and so forth. It's a scalar for exactly the same reasons. Once you know that the a's transform the same way as the x's, x and t, then by the same little bit of algebra, you can see that the difference of the squares of the time component and the space component will not change under a Lorentz transformation. It's the same little bit of algebra to see that dt squared, dt squared minus the x squared minus so forth, minus dy squared. Once you know that little bit of algebra, in fact, we can write it as tau squared is equal to t squared minus x squared minus y squared minus z squared. For the same reason that this doesn't change under Lorentz transformation, neither does this. So we have now constructed a scalar. Difference of the squares of the time components and the space components. Right? The last point is that given a scalar, you can construct a 4 vector out of it, not by just looking at it, but by differentiating it. By differentiating it with respect to the 4 components of space and time, those 4 derivatives form a 4 vector. All right, so a special case of a 4 vector, given a scalar, are the collection of components, the derivative of phi with respect to x mu. Derivative of phi with respect to t, derivative of phi with respect to x, derivative of phi with respect to y, and so forth. These form a 4 vector. Not surprisingly, these form a 4 vector. And so now we have a set of tools for creating Lagrangians. Oh, well, yes. We know how things transform, and we know how to build scalars and vectors out of other objects. What's the rule for making a Lagrangian or an action invariant? It's very simple. We require that the Lagrangian itself is the same in every coordinate frame. That the Lagrangian, the thing that we add up over all these little cells, is the same in every coordinate system. Okay. That means it's a scalar. That just means it's a scalar. That the Lagrangian should be a scalar. So that's our rule. The Lagrangian should be a scalar under Lorentz transformations. It's not scalar, scalar. And that's all that there is to it. You take your field, which happens to be phi in this case, and you consider all the possible scalars that you can make out of it. And they are possible candidates to put into the Lagrangian. So let's start with some. I'm running out of blackboard space. I guess I don't need this anymore. What can we make? Well, phi itself is a scalar. Okay. But not only is phi a scalar, but any function of phi is a scalar. If everybody agrees on the value of phi, they will also agree on the value of phi squared, phi cubed, the hyperbolic cosine of phi, the functions of phi will also be scalars. So any function of phi is also a scalar, and therefore it's a candidate for something that you can put into the Lagrangian. Well, we've already done that. Right over here. Now, next, what else can you put in? Well, we certainly want to put in derivatives of the field. If we don't put in derivatives of the field, our field theory is going to be very, very trivial. It's not going to be very interesting. We have to put derivatives in, but we have to put the derivatives in a way which constitutes a scalar. So what can we do? Well, it's easy. We just start with the vectors that we can build, d phi by dx, dx mu, that's a vector. And we simply construct the invariant, or the scalar, out of the components of the vector. So what does that mean in practice? It means d phi by dt squared minus d phi by dx squared minus d phi by, I get tired of writing it. I wish I had a shorthand notation for it. No? All right. No, it's not the Laplacian. The Laplacian is the second derivative. This is the first derivative. The Laplacian is like an acceleration. Right? The Laplacian is a different thing. This is the sums of the squares, or the difference of the squares. So there's something you can put into the Lagrangian, and you can be sure that when you do, the equations that you get out are the same in every reference frame, just because this quantity is the same in every reference frame. In other words, it's equal to the corresponding thing in another frame. Right? So here's, are there other things you could write down?
What about mass? That's a scalar.
Yeah, but mass is not a, sure, but mass is just a parameter. It's not a dynamical thing. You can certainly put the mass in there, but mass of what? Whose mass? You can put numbers in. Yeah, numbers are perfectly good things to put in. Okay? We did that already. We said, look, let's take v of phi to be mu squared over 2 phi squared. We put a number in. So yes, you can put numbers in. Just numerical constants. Well, here's something else you could do. Now this would start to make a complicated story, but You could take this, which is a scalar, and you could multiply it by another scalar. Multiplying scalars together gives scalars. Multiply two things, each of which is the same in every reference frame. Multiply them, it is still a scalar. So we could multiply this by some function, if we like, of phi. That's a legal thing to do. It starts to make a rather complicated Lagrangian, and we're not going to consider it for the moment, but it's certainly a reasonable thing, Lorentz invariant thing to do. We could do something even uglier. This would get very ugly. We could take this scalar here and square it, and have higher higher powers of derivatives. That begins to get very ugly, in fact, and it's not a thing which appears in very often.
In principle, you could add the higher order derivatives, couldn't you? As long as you make them a scalar.
In principle, you could, but not within the confines of the rules of classical mechanics. Rules of classical mechanics, you can have functions of the coordinates and their time derivatives. So if you're staying within the boundaries of standard classical physics, you want to stay with just first derivatives, and higher powers of first derivatives, but only first derivatives. Okay. All right, so once we do that, we now see why this was, why I chose it the way that I did. Of course, to restore the units, we would want to put a 1 over c squared here. And purely for notational reasons, meaning, say, purely for conventions, we put a 1/2 there in front of the whole thing. It's the same 1/2 that goes in front of 1/2 mv squared. You didn't have to do it 1/2 mv squared. You could have taken the Lagrangian to be mv squared. Of course, then the mass would have differed from Newton's mass by a factor of 2, but that's okay. You could have done it that way. It's a convention. It's a convention that F equals ma and not F equals twice ma. That's a convention. So this 1/2 is purely a convention. There's no content in it. But once you fix it, you fixed it. All right. So our example, the example that, that we'll focus on will be this one over here. I'm going to write it over again over here. I'm going to leave, let's see, I'll leave the c there for the moment, minus, let's take mu squared over 2 phi squared. That's our simplest field theory. In fact, it's even simpler if we don't have this term there, if we only have this. And it's a very simple field theory. And it's a wave equation. It gives rise to a wave equation. I've written down, where did we write the equation? We did write the equation, but I've lost it. Yeah, so let's just write down what the wave equation that derives from this is. It is 1 over c squared d second phi by dt squared. That's like acceleration. Then there's an analogous term for each one of the x, y, and z with a minus sign. D second phi by dx squared plus y squared plus z squared. And then from here, we get plus mu squared phi equals 0. And that, as I said, is a wave equation. It's a particularly simple wave equation because it's linear. Everybody know what linear means? It means that the field and its derivatives only appear to the first power. There are no terms in it like phi squared or phi times derivatives of phi, only things to the first power.
Question, because that basic equation was derived from the metric where tau is invariant, can you say that in this system that is the invariant metric that defines it? Would that make sense? Thinking of it as a metric of distance,
Metric of this,
that's always
yes.
constant, or not, scaling.
Well, I'm not sure which metric you're talking about. You're talking about the metric of space stuff?
The a squared, the
Yeah.
tau, well,
Yeah.
tau equals t squared minus x squared.
Yes. That's right. I mean, it is certainly connected with the metric. We haven't used the terminology metric for space-time. We will when we get to general relativity, but yes, that's what it's about. It's about the metric of space-time. Absolutely. Yeah. Yeah. The metric of space-time is dt squared minus dx squared minus dy squared minus dz squared. Absolutely. Any other questions at this point? Yes, sir.
Where you define four vector, is there something more general where y and z components aren't just equal?
Well, the y and z components aren't just equal. Oh, well, it wouldn't be a four vector then. I can't think of anything like that which would just have four components. No, I don't know anything like that. Now, of course, what you can have, the scalar is a thing with only one component. It's only got one component. It's not an x component, it's not a y component, it's not a z component, it's not a t component, it's just the scalar. The vector has four components labeled by x, y, z, and t. Of course, there are more complicated things, tensors, which have multiple components with xx components, xy components, tx components, and so forth. But fortunately, we don't have to deal with them for most of classical field theory, not until we get to general relativity anyway. So, yeah.
This, I think, maybe is related to the last question. In general here, y and z are being held fixed, so any Lorentz transformation just involves x and t. But I mean,
Well,
couldn't you have the space dimensions
rotated.
getting involved in the whole thing so that it gets more complicated?
Yeah, I mean, that's right. And you can have, that's right. You could, first of all, you could have a Lorentz transformation not along the x-axis, but along the y-axis. In that case, the transformation laws, let's think about a Lorentz transformation along the y-axis. This would be a transformation in which two coordinate systems were moving along the y-axis. Then the transformation properties would be exactly the same, except that wherever you saw x, you'd stick y. So you'd have t prime is equal to t minus vy over square root 1 minus v squared. X prime equals x. Y prime equals y minus vt over square root. And z prime is equal to z, period. All right, so and of course you got a much more complicated things. You could have Lorentz transformations where the frames are moving along some funny axis, which isn't along the x, y, or z axis. But these are all simply rotations of the same thing, where you first rotate your axes, and then you do what you would have done had you been doing a transformation along the x-axis. So that's the general Lorentz transformation. The general Lorentz transformation is a combination of rotations of space and transformations along the x-axis. Every Lorentz transformation can be built up by thinking, by a Lorentz transformation, now I mean in an arbitrary direction, any two frames which are related by an angle in space and which are moving relative to each other in any old direction, that transformation can be built up out of a combination of rotations of space first, and then a transformation along the new x-axis, and then another rotation of space. The point is that as long as you make sure that your theory is invariant with respect to the simple Lorentz transformation, let's say the X, where is it? The X Lorentz transformation. As long as you make sure that it's invariant with respect to this and with respect to rotations, then you're in business. Then you're in business. It will be invariant with respect to any Lorentz transformation at all. Well, that's an interesting question. Now, let's come back. Where is our Lagrangian? Here it is. Is this invariant with respect to rotations? Let's forget Lorentz transformations. How about rotations? Yes, because this is the sums of the squares of components of a space vector. You know, it's like x squared plus y squared plus z squared. That's rotationally invariant. So yes, this is invariant not only with respect to the Lorentz transformations along the tx axis, but also with respect to rotations of space. And that's enough. That's all you have to keep track of. If you know that your expressions are invariant with respect to spatial rotations and also Lorentz transformations along one given axis, you're finished. You're, or maybe I should say you're beginning. Right. All right, so do we have the basic rules for classical field theory? You take your fields, whatever they happen to be. You figure out all the scalars that you can make out of taking the fields and their derivatives. The fields don't have to be just scalars. We're going to take examples where the fields themselves are not just scalars, but also vectors, maybe even tensors at some point. And you build out of them and their derivatives all of the scalars that you can create. Once you have all the scalars you can create, then you build the Lagrangian and terms of those as functions of those scalars, for example, sums of terms. And then you apply the Euler-Lagrange equations. And those give you the equations of motion, or the field equations, describing the propagation of waves, whatever it is that that field theory is supposed to describe. Now, at some point, we will come back and study the wave equation. I keep losing it, but we'll study the wave equation, solve it, and understand that it does give rise to wave motions. But before we do that, I want to do one last thing tonight. Are we exhausted? If we're exhausted, we can quit. Yeah.
Question. It seems like there's a lot of freedom that you have here.
Oh, immense.
Just like construct scalars until you go,
Right.
without end,
Right.
and come up with Lagrangians without end. So are those all going to give you physically meaningful results?
Those are all going to give you, not quite. There are some rules that I haven't expressed yet. There are rules about, there are rules that come from classical mechanics, which we haven't talked about, but modulo some special rules that we haven't discussed. Yeah, they all give you classical mechanical systems that make sense. Almost all of them don't survive the transition to quantum mechanics. That's where the fun happens. When you try to make the transition to quantum mechanics, you find that almost all of them, all but a tiny set of measure zero, just are inconsistent. Give infinite answers, give nonsense of one form or another. And those are, of course, the ones that don't give nonsense, which are the ones that you focus on. But at the level of classical physics, yes, there's just an enormous ambiguity.
Does field have to be continuous?
Fields? Yeah, let's say fields should be continuous. If they're not continuous, that means they have infinite derivatives. And if they have infinite derivatives, then they'll have infinite action. We haven't spoken about energy yet, but they'll have infinite energy. Next time we'll come back to the energy stored in a field. But I wanted to spend another 15 or so minutes talking about the relation between particles and fields. Now, I'm not talking about the quantum mechanical relation between particles and fields. I'm just talking about the relation between ordinary particles and how they interact with fields. If I had worked out the rules for electrodynamics instead of for a simple scalar field theory, I might tell you how charged particles interact with an electromagnetic field. We haven't done that yet. We'll come back to that. But let's talk about how a particle might interact with a scalar field, with this scalar field phi. How might it interact with it, and how might the presence of the scalar field affect the motion of the particle? Okay. For that, we need a Lagrangian. And there are many, many possible Lagrangians we could write down for the same reason. Classical mechanics simply doesn't have enough constraints in it to tell you in detail what the Lagrangian has to be, but we have some rules. Let's think about the Lagrangian for a particle moving in the presence of a pre-established field. Somebody has solved the equations of motion for the field, and we know the field phi of x and t. It's some specific function of space and time. Now a particle is moving in that field. That particle might be coupled to the field. It might be like a charged particle in an electromagnetic field. How does the particle move? Well, to answer that question, we ask what kind of Lagrangians. I wish this guy would go away. Go away.
West Nile virus coming at you.
Thank you.
And with the erase.
What? No, I'm a gentle person.
Mosquito.
You think it's a mosquito? It doesn't look like a mosquito. It's just too big to be a mosquito. It's not a mayfly. I know mayflies very well. All right. So let's go back to particle mechanics, but particle mechanics in the presence of a field. Okay. So first of all, we've already written down a Lagrangian for a particle. It was about the only thing available that was invariant, and it was the integral of d tau. For reasons of convention, well, not just for reasons of convention, but there was a parameter here which was called the mass, which turned out, in fact, to be the mass. We discovered that it behaved, this is tau. It behaved like the non-relativistic mass when the particle was moving slowly. And there was also a minus sign. Surprisingly, there was a minus sign there. It always surprised me when I was a young person learning this. Why do you put the minus sign there? Well, you put the minus sign there so that when you work it out and look at slow motion, you get the right non-relativistic answer. But this was it. And d tau was the square root of dt squared minus dx squared. I won't write, I keep telling you over and over again, I won't write dy squared and dz squared, and then I do it anyway. Well, I'm not going to do it. Okay. And then we divided by dt squared, put the dt out here, made this 1 minus dx squared over dt squared, dx by dt squared. And that was our Lagrangian. It's a function of velocity. We can also call this a velocity squared. Also terms for y and z. Okay. This was our Lagrangian. If we expanded it out for slow velocities, we found out that it was the good old Newtonian Lagrangian, good old conventional Lagrangian. But this was it for relativity. Now, what can we do to this to allow the particle to couple to a field, allow the particle to interact with the field, be affected by the field? Well, in order for the particle to be affected by the field, we have to put into the Lagrangian the field somewheres. We have to put it in a way that is Lorentz invariant. In other words, we want to put it in a way which is the same in every reference frame. The only thing we have around involving fields, which is the same in every reference frame, is scalars. There's lots of things we could do with scalars, but one very simple thing we could do would be, well, this was minus m d tau. The simplest thing you can do is you can say, as the particle moves through the field, you can add another term here, which is the field times d tau. There are many other things. This is not unique by any means. First of all, you could add the square of the field times d tau, or the cube of the field times d tau. All of these would be quite legitimate. Any function of the field times d tau. But as far as the particle motion goes, since we want to use invariants, quantities which are invariant, we want to use d tau. It's the only thing around involving little steps along the trajectory which is invariant. So a possible Lagrangian would be to add minus m plus some function of the field phi. Let's just call it plus phi. There would be a possible Lagrangian for a particle moving in a pre-established field. For the moment the field has been given to us, we're not going to ask how it got to be the way it was. We're asking, how does the particle move in the field? This is kind of like asking how a particle moves in a magnetic field or an electric field. You write down a Lagrangian for the particle in the electric or magnetic field. You don't worry about how the electric and magnetic field got that way. Okay. And this would be phi of x and t. All right, I'm doing this, first of all, to illustrate a point about connection between particles and fields, but second of all, just as in order to do a little exercise and to work out the equations of motion of the particle. Let's work out the equations of motion of the particle. Here's its Lagrangian. And to work out its equations of motion, we just do the Euler-Lagrange equations of motion. Let's just do them. They're ugly. They're not nice. They're not pretty.
Does phi have to be in the integral?
Yes, I'm sorry. Phi should be in the integral. Absolutely.
Unless it's a function of only x, right?
Yes. Unless it's a function only x. That's correct. Unless it happens to be just a function of x.
But that x represents the position of the particle.
This represents the position of the particle at the time t. Yes, it should be in the integral. It has to be in the integral. Because even though phi might not depend on t, x depends on t. So phi of x depends on t. So it's phi of x and t, and it's inside the integral. Right. Now, first of all, notice something interesting about this. Supposing for some reason the field liked to migrate to some value, for some reason the field liked to seek some stable value which wasn't 0. Supposing it liked to get frozen for some reason away from 0. Constant, completely constant. Phi would then just be a constant, or approximately a constant. The motion of the particle would be absolutely identical to a particle whose mass was m minus phi. It would be exactly the same as if the particle mass was m minus phi. Why minus? Well, it's minus m plus phi, so the mass would be m minus phi. This is the simplest example of how a scalar field can give rise to a shift of the mass of a particle. I said there was going to be an exam at the end. What field is most like this in nature? The Higgs field is the thing which is most like this scalar field in nature. And you can see how it's possible that if the Higgs field gets shifted by some mechanism, its value gets shifted, in turn it will shift the value of the mass of a particle. In fact, if the mass of some particle naturally began as 0, but it was coupled to this field phi, and this field phi naturally sought some particular value, the particle would effectively have a mass which would be related to this field phi. So this is not exactly the Higgs mechanism, but it's closely connected with it. And it's roughly what's meant when people say the Higgs field gives the particle mass. The Higgs field enters into the equations as if it were part of the mass. Okay, but let's just see what the equation of motion would be. And then maybe we'll try to take the non-relativistic limit. You know, I don't think I've done this for years. I don't even remember how it goes. Let's do it. Let's try it. Okay, so here's the Lagrangian. And phi now is just thought of as a function of x, a function of the position at a time t. All right, so the first thing to calculate is the derivative of the Lagrangian, partial derivative of the Lagrangian with respect to x dot. Here's x dot right here. What is that? That is m minus phi of x and t times x dot over the square root of 1 minus x dot squared. I'm doing this as if there was only one direction of space. We'll make it simple. We'll make it a problem moving in which a particle moves in only one direction, namely the x direction. Let's keep y and z out of it. Where did I get this from? Well, if you remember the last time, we calculated the momentum by differentiating the Lagrangian with respect to x dot. And what do we get? Remember what we got? We got the mass times the velocity over square root of 1 minus v squared. Remember that? That was the momentum. And it was equal to the derivative of the Lagrangian with respect to the velocity. So if I differentiate the Lagrangian with respect to the velocity, we'll get exactly the same kind of thing, except every place you saw m, there will now be m minus phi. We could do it explicitly. To differentiate this with respect to the component of the velocity, we differentiate the square root, we multiply by this. This is what you get. Not m times the velocity, but m minus phi of x. So that's the first step. What's the next step? We differentiate this with respect to time. Right? So the next step is differentiate this with respect to time. This is d by dt of m minus phi x dot over square root of 1 minus x dot squared. That's one piece. Then what's the other term in Lagrangian's equations? Or the Lagrange equations?
If you're differentiating with respect to time, what about the phi of x and t?
You'll have to differentiate it. We'll do it in a minute. Right, but what's the other term? Minus dl dx. Does x appear in this Lagrangian? Yes, it does. It's in phi. Phi depends on x and t. So that's equal to minus derivative of phi with respect to x, or I suppose it's a partial derivative, minus partial derivative of phi with respect to x times, let's see, where's the Lagrangian? Yeah. We're differentiating the Lagrangian with respect to x. Here's the only place that x appears. But this thing multiplies the square root, so the square root is still there. Square root of 1 minus x dot squared. That's it. That's the equation of motion. It's a differential equation. The left-hand side has something which is more complicated than an ordinary acceleration. There's a d by dt. Well, it has all kinds of terms in it. It's a nuisance to work out. It's not pretty. But this is it. Let's work it out. Let's work through a little bit of it. Okay. So first of all, we get, I wonder if we can figure out where the speeds of light go. I'm not going to do that now. I don't want to do it now.
Why is d phi dx multiplied by the square root of 1 minus x dot squared, as opposed to x dot squared over the square root of 1 minus x dot squared?
Well, the Lagrangian had phi times the square root of 1 minus x dot squared. That was in the Lagrangian, right? Was it with minus sign? No, it was with the plus sign. It was minus m plus. Okay? When I differentiated phi with respect to x, it still contained the factor, right? Okay, so that's there. This is not pretty. This is not the... It's nice to wind up a lecture with a nice, beautiful, elegant result. This has not happened in this case, and I knew that wouldn't happen. But let's just see what's here. First of all, the d by dt can hit this thing over here. Now, this thing over here is what would have been the canonical momentum had this term not been. Well, it is what it is. It is what it is. So you get a term which is d by dt of x dot over the square root of 1 minus x dot squared. That in itself is not very pretty. That's when the d by dt hits this term times m minus phi. That's the derivative acting on this factor times m minus phi. And then another term which is plus, we have to take the derivative with respect to t of minus phi. M is a constant. M is a constant. The derivative with respect to t of minus phi. That is minus, let's first write it as phi dot times x dot over square root of 1 minus x dot squared. That's gotten from differentiating this. And that's still equal to the right-hand side. d phi by dx with, I guess, a minus sign times square root of 1 minus x dot squared. All right, but what about phi dot? What can I do with phi dot?
You have to have x dot in the, because it's also, x is also a function of time, right? So you have to take partial phi, partial x times x dot.
Let's take a simple case where phi only depends on x, just to be simple. Phi only depends on x, just to simplify the story. Then, is phi dot equal to 0? No. It's not 0 because it depends on x, and x is not constant. All right, so what is phi dot? Phi dot then is equal to the derivative of phi with respect to x times x dot. All right, so this is then going to be from here d phi by dx, and there'll be an x dot squared here. I'm not going to try to make it any simpler than this. It's a bit of a monstrosity. I'll leave you the exercise of putting the speeds of light into it. No, there's a point. Put the speeds of light into it, and then study it when the velocity is much slower than the speeds of light, and see if you can recognize anything familiar about it. See if you can recognize anything familiar about it. It should be familiar in that case. Okay, so put the speeds of light in, and then take the limit in which the velocity is much slower than the speed of light. You'll find a pattern. The pattern will be a familiar thing.
For more, please visit us at stanford.edu.